Imagine you have slipped the bonds of Earth, drifted past the outer planets, and found yourself floating through the interstellar void. Suddenly, the starlight around you begins to warp and bend. You are caught in an invisible current, accelerating toward a region of absolute darkness. If you fell in, would you be crushed instantly by the weight of 1,000,000,000 suns? Does your perception of time grind to a complete halt while the rest of the universe ages and dies without you? Could you survive the descent, or does the center lead to another universe entirely? Physicists treat these scenarios as the inevitable conclusions of the same mathematics that keep our satellites in orbit. Today, we are diving into the physical reality of a descent into the dark, tracing the boundary where our standard understanding of the cosmos reaches its limit. To understand what waits in the dark, we have to look at the massive stars that create these voids. A black hole is the tombstone of a massive star. For millions of years, a giant star survives through an intense balancing act. Deep in its core, nuclear fusion pushes outward, while the staggering mass of the star's own outer layers pushes inward with crushing gravity. When the nuclear fuel runs out, the outward pressure stops. In a fraction of a second, gravity wins. The entire mass of the star collapses inward, rebounding in a supernova explosion. But the dense core left behind continues to shrink, condensing a mass several times greater than our Sun into a single microscopic point. This runaway collapse creates a gravitational pull so absolute that the velocity required to leave its surface exceeds the speed of light. Because nothing in the universe travels faster than light, nothing can escape. The gravity becomes a trap door in the structure of space itself, creating an environment where the reliable rules of the physical world break down. This image from a National Science Foundation press conference provided the first direct visual evidence of a supermassive black hole located in the galaxy M87. To capture this shadow, scientists networked observatories across the globe, creating an Earth-sized telescope array. It proves that these mathematical anomalies exist as physical objects in our sky. We also confirm their existence by measuring the vibrations of space-time itself. This long concrete tube belongs to LIGO, a detector designed to measure gravitational waves. When two black holes collide, they send ripples through gravity that travel across the universe. By the time these ripples reach Earth, they stretch and squeeze this facility by a distance smaller than the width of a single proton. Look at this animated comparison to see the scale of the largest known examples. We begin with our Sun, zooming out past the orbits of Mercury, Earth, and the gas giants. If we place the black hole TON 618 in the center of our solar system, its physical boundary would swallow everything. TON 618 contains the mass of 66 billion suns. It is so wide that light takes weeks just to cross its radius. We can photograph their shadows and measure the shock waves of their collisions from billions of light years away. But these observations only describe the exterior. To understand the physics hidden beneath their surface, we have to cross the boundary where light itself becomes trapped. Your descent begins millions of miles from the center as you enter the accretion disk. This is a turbulent halo of superheated gas and shredded star matter orbiting at a fraction of the speed of light. As these particles race around the center, they create immense friction, heating the gas to tens of millions of degrees and emitting lethal levels of X-ray radiation. Pushing through this plasma, you arrive at the photon sphere. Here, the gravitational pull is so strong that it captures light, but not yet strong enough to pull it immediately inward. Instead, gravity forces photons into a circular orbit around the dark center. This path creates a mind-bending visual distortion. If you were to hover at this boundary and look straight ahead, the light bouncing off your own back would be caught by the gravity well. That light travels in a complete circle and returns to your eyes. At the photon sphere, looking straight ahead allows you to see the back of your own head. Surviving this storm of light and gas brings you to the threshold of the event horizon. You are about to reach the point of no return. The event horizon is the absolute boundary of the black hole. At this exact perimeter, The gravity is so intense that the velocity required to escape exceeds the speed of light. Since nothing travels faster than light, anything that crosses this line is permanently disconnected from the rest of the universe. Einstein's equations describe gravity as the physical geometry of space and time, a fabric that bends and stretches in the presence of mass. Because the gravity at the event horizon bends space so severely, it also distorts the flow of time. This split screen shows the paradox created by that distortion. If an outside observer watched you fall, your movements would appear to slow down as gravity stretches the light returning to their telescope. They would see you freeze at the edge. Over thousands of years, your image would gradually fade to red as the photons lose energy, eventually disappearing from view. Your own experience is different. Time feels normal, and you feel no physical barrier as you pass the event horizon. But looking back at the universe you are leaving, the incoming light is heavily compressed. You would see the entire future history of the outside universe playing out in rapid forward motion, watching stars burn out in a matter of seconds. Once you are inside, all possible paths through space curve toward the center. There is no physical direction that leads back to the horizon. Because the path toward the singularity is now inevitable, the direction inward functions exactly like the direction future. You can no more turn away from the center than you can turn away from tomorrow. Space and time have effectively traded their properties. Now cut off from the outside world, your descent continues. The gravitational pull increases at an exponential rate, with every millisecond. You are now experiencing tidal forces, where the strength of gravity changes drastically over very short distances. This diagram illustrates spaghettification. Because you are falling feet first, your feet are closer to the center than your head. In a normal environment, this difference is unnoticeable. But deep inside a black hole, the gravity on your feet becomes millions of times stronger than the gravity on your head. This difference stretches your physical body until the chemical bonds holding your cells together snap. Muscles, bones, and molecules are ripped apart by the differential in force. Within seconds, your structure breaks down into a continuous stream of subatomic particles, stretching into the dark. Your biological form is destroyed, but the fundamental quantum information that makes up your particles cannot be easily erased. That data continues its journey toward the absolute center. At the very bottom lies the singularity, an infinitesimally small point where all the mass of the black hole is crushed together. The mathematics suggest its volume is zero and its density is infinite. When physicists encounter infinity in their equations, it means our current laws of physics have failed to describe reality. We have followed the equations of general relativity as far as they can go. But beyond this point, nobody knows what happens. The center of a black hole remains the most closely guarded secret in the natural world. Theoretical physicists have proposed several hypotheses to explain this boundary. Some suggest the singularity is a bridge to a white hole in a different region of spacetime. Others propose the holographic principle, the idea that a 3D object falling in never reaches a center, but is instead smeared as two-dimensional data onto the surface of the event horizon. The fate of this data is a subject of intense debate. Stephen Hawking showed that black holes leak subatomic particles at their edges. Over trillions of years, through this Hawking radiation, a black hole will slowly evaporate. This creates the information paradox. If the black hole disappears, is the data it contained permanently deleted from the universe? This paradox is the unresolved battleground of modern physics. It pits general relativity, which describes the gravity of heavy objects, against quantum mechanics, which describes the subatomic world. They work perfectly on their own, but inside the singularity, they contradict each other. Researchers are using next-generation instruments, like these radio telescope arrays, to peer deeper into active galaxies. By combining observational data with advanced artificial intelligence, astronomers are working towards bridging the gap between the subatomic world and the cosmic one. Future deep space missions may one day allow robotic probes to fly closer to these anomalies, gathering data from the outer edges of the accretion disk to confirm if our mathematical models align with physical reality. Seeking the center of a black hole reveals the limits of human comprehension. We have mapped the human genome and split the atom, yet when confronted with dying stars, our equations produce numbers that defy logic. The black hole is a reminder that the cosmos is under no obligation to be easily understood. The event horizon keeps the truth securely locked in the dark. Perhaps the greatest mystery isn't what's inside a black hole, but whether the universe is hiding an even larger secret beyond it.